Earth might have just one natural moon, but every so often, small objects wobble into a similar orbit and accompany our planet for extended periods. NASA has recently confirmed that a faint asteroid, 2025 PN7, measuring 19 meters, is doing precisely that. It trails the Sun almost in sync with Earth, making it a newly identified quasimoon. While it won't affect tides or be visible in the night sky, its prolonged presence provides scientists with a valuable opportunity to study how smaller bodies behave within Earth's orbital space. In this video, we will delve into what 2025 PN7 is, its significance, and the expectations scientists have moving forward. Let's dive in. The identification of 2025 PN7 originated from routine sky monitoring efforts. Observatories like the Pan-STAR survey in Hawaii scanned the same areas repeatedly, each night, using wide-field imaging systems to detect faint and slow-moving objects. In August 2025, one of these subtle detections piqued astronomers' interest. It moved slowly enough to suggest proximity to Earth, but its low brightness indicated a very small size, roughly 19 meters across. After being flagged, the object was monitored over several nights to refine its position measurements. These data points were subsequently inputted into orbital determination software, where the object began to distinguish itself. Unlike typical paths of near-Earth asteroids that briefly cross Earth's orbit before continuing on their way, 2025 PN7's orbital period closely mirrored that of Earth. That initial correlation, with a period of one Earth year, is indicative of a potential quasimoon. NASA's Center for Near-Earth Object Studies fine-tuned the orbit with additional data. The object's trajectory around the Sun remains in close alignment with Earth over the course of a year, creating a co-orbital relationship known as a one-to-one orbital resonance. Unlike a captured moon, it is not tethered to Earth's gravity. Instead, this resonance allows it to linger near our planet for extended intervals, all while both entities independently orbit the Sun. Simulations run forward and backward in time, painted an even more intriguing picture. It appears that 2025 PN7 likely entered Earth's co-orbital zone around the 1960s, suggesting it has accompanied Earth for decades unnoticed. According to current models, it is expected to maintain this relationship until approximately 2083, granting scientists several more decades of stable study. Despite this long-term behavior, 2025 PN7 is exceedingly dim. Its small size and dark surface reflect minimal sunlight, which explains its long evasion for detection. It was only through advancements in automated sky surveys and consistent nightly monitoring that this discovery was made possible. The recognition places 2025 PN7 within a small group of known quasimoons, although most in this category are larger or follow more stable paths. While this new object is modest, its presence provides a rare opportunity for long-term access to a co-orbiting body. These extended observations allow astronomers to detect subtle changes in its motion and refine theoretical models of how such objects behave in Earth vicinity. In summary, the discovery of 2025 PN7 illustrates that Earth's orbital surroundings are more intricate and populated with small temporary companions than previously believed. The importance of asteroid 2025 PN7 is less about its size and more about the orbital configuration it occupies. Quasimoons like this one offer scientists a natural laboratory to investigate how small bodies evolve under a planet's gravitational influence without being gravitationally captured. A core interest is the one-to-one orbital resonance with Earth. Since both Earth and 2025 PN7 orbit the Sun in nearly identical time frames, their motions remain synchronized. However, this synchrony is fragile. Small bodies are persistently affected by gravitational pulls from multiple planets, as well as non-gravitational forces like solar radiation. Monitoring how PN7 reacts to these influences over decades can help refine models that describe the longevity and stability of co-orbital objects. Scientists are particularly eager to examine the Yarkovsky effect, a subtle but constant force that occurs when sunlight heats an asteroid's surface, causing the radiated heat to produce a slight push. Over lengthy intervals, this force can shift an asteroid inward or outward in relation to the Sun. Since PN7 is expected to stay near Earth for many decades, astronomers will have an unusually long observational period to assess how this effect modifies its trajectory. Long-term observation of such objects enhances predictions for the future paths of other near-Earth bodies. The origins of quasi-moons also spark interest. Some may migrate from the asteroid belt and get temporarily co-captured via gravitational interactions, while others could be fragments resulting from collisions elsewhere in the inner solar system. Though 2025 PN7's small size and dimness currently limit detailed spectral analysis, potential future technologies might determine whether its composition aligns with known asteroid families or represents a unique sample from a different region. Quasimoons are also promising candidates for mission planning. Their slow relative speed concerning Earth renders them easier to reach and navigate around than many main-belt asteroids. For engineers, they present stable, low-risk environments for testing autonomous navigation, precision maneuvering, and short-range sampling technologies. Although PN7 is small, its prolonged accessibility provides mission planners with the flexibility to consider it a viable target for future experiments. Overall, 2025 PN7 offers a rare chance to observe a co-orbiting body over an extended period, allowing scientists to link theoretical predictions with genuine long-term behaviors. Its presence enriches our understanding of how small objects traverse Earth's vicinity and how resonant dynamics influence the population of near-Earth entities. The enduring presence of 2025 PN7 carries numerous implications for research, exploration, and comprehension of the near-Earth environment. One significant advantage is the opportunity for prolonged monitoring. As PN7 remains close to Earth until the 2080s, it enables researchers to investigate gradual alterations in its orbit due to gravitational interactions and solar radiation. This type of dataset is incredibly valuable, as most near-Earth asteroids are only observable during brief flybys lasting weeks or months. An extended observational window aids scientists in testing and refining models predicting the behavior of other smaller bodies that may traverse Earth's path. Another implication pertains to mission opportunities. While the size of PN7 restricts the types of missions suitable for it, its slow relative motion allows for easier and less fuel-intensive access compared to more distant targets. A spacecraft could trial autonomous navigation, approach techniques, or surface interaction experiments in a controlled setting. Such capabilities are becoming increasingly vital as space agencies and private enterprises explore asteroid deflection techniques and resource mapping technologies. Testing these systems on a stable, nearby object could provide invaluable real-world insights. The discovery of PN7 also underscores the dynamic nature of Earth's orbital region. Many envision the space surrounding Earth as predominantly vacant. However, findings like this illustrate a more vibrant environment. Small objects flow in and out of co-orbital states, influenced by resonances and long-term gravitational interactions. Understanding how these populations move sharpens impact risk assessments and enhances models predicting the movement of both dust and larger entities throughout the inner solar system. Looking ahead, advancements in survey technologies are anticipated to unearth more quasimoons. Future wide-field telescopes paired with improved detection algorithms will be capable of identifying smaller and fainter objects than ever before. Each discovery contributes new insights to the broader narrative of how small bodies evolve near planets, and how resonances generate temporary companions that can endure for decades or even centuries. The main takeaway for the public is clear. 2025 PN7 is scientifically engaging but completely harmless. It poses no risk to the night sky, will not impact Earth, nor will it affect natural processes like tides. However, its existence serves as a reminder that Earth's orbital neighborhood is more intricate and dynamic than it appears, with smaller companions occasionally joining us on our solar journey. While 2025 PN7 is a modest companion, it provides a valuable long-term perspective on Earth's orbital surroundings. Its protracted presence aids in refining our understanding of how small bodies move near our planet, making this quiet visitor a significant source of insight for years to come.